Howdy, folks. Friday for us, right? I know. All right. So, today we got our quiz, but also before that, I want to talk you through just one formula of kinematics. Okay? Kinematics is a formula, again, or a set of formulas that we're going to use that helps us to kind of find a few different things. All right? So, here we go. All right. So, kinematics, the purpose of these formulas, as you can see here, are to provide a way to determine object's motion. If we know acceleration, initial velocity, final velocity, distance traveled, or time taken. Those are the big ones for us, all right? Meaning that instead of being locked into finding just velocity from distance over time or acceleration from change in velocity over time, now we can actually use more kind of variables to be able to find answers to problems that are out there for us, okay? So this is our first one. Again, make sure you write this down somewhere, circle, star, highlight. If you want to put this in the front of your notebook, something like that, absolutely fine. All right, goes VF squared equals VI squared plus 2A delta D. Your velocities have to be meters per second. Your acceleration has to be meters per second or meters per second squared, and your distance has to be in meters. Those are ones that we have to convert to. All right, so if we get kilometers, got to fix it. If we get miles per hour, got to fix it. Okay, so here's what I want to do. Okay, I want to show you how we get these, because all too often I feel like people look at these formulas and say, okay, great. Is this actually a real tangible formula? How does this actually become the formula that we see in front of us? And I'm not asking you to ever do this again. I'm just asking you to sit back, look at it, and just see how we play this out. Okay? Do not write any of this. Do not write any of this. Do not write any of this. Okay? Here we go. So we're going to start with our average velocity equals our change in distance over time. If we look right now, we see change in distance is a big one for us because that's in our formula up above. All right. So what we're going to do is we're going to start by expanding what velocity average is. So that's the only thing that has any ability other than our distance to be changed. Okay. Average velocity, if you remember, when we calculated average time on our graphs, or on our data tables for lab 1-2 and 1-3. That's just the number of velocities divided by 2. So in this case, it's just a final and an initial divided by 2. When we plug that thing in, that's what we start to see, right? VF plus VI over 2 equals delta D over T. As we start to look, we start to see some familiar faces. VF is there, VI is there, we got the 2 and we got the delta D, right? At this point, I don't like fractions, so I'm going to clean that up a little bit. Multiply both sides, or cross multiply and divide, sorry. So VF plus VI times T equals 2 delta D. Now that right side looks pretty darn familiar. We just need an acceleration in there somehow, right? So when we see this, it's pretty close. If we can replace T, then we have something for it, meaning that it looks similar, it might look more similar to that. So here's how we do it. If we want to add an acceleration, well, that also allows us to get rid of that time. Because if you look at the formula on the bottom here, right down here, right here, right? It's got a T, but it doesn't have an A. So what we have to do is be able to sub out the time for the acceleration. So that's where this formula comes into play for us, all right? So put it over 1 so I can cross multiply and divide. Multiply A times T, right? And that's equal to VF minus VI. If I have AT equal to this, VF minus VI, divide by A, and I get that. Now what I can do is I can sub out T, and I can get that acceleration into my formula. Okay? So when I do that, it looks like this. VF plus VI, that together, quantity of that, times VF minus VI, all right, over A. So hopefully you're able to see, well, that looks pretty close, right? If I put that over 1, now what I can do is multiply or cross multiply and get my stuff off the bottom, so get it out of the denominator. So I'm going to be able to move this A right over there, okay? Now, if I do some FOIL, first out in last, right? First out in last, what I end up seeing is VF squared minus VI squared. because I'm gonna have one where I add VF times VI, one where I'll subtract VF plus VI. All right. So at this point, that looks pretty similar to that. The 2AD looks pretty close. Add over our VI squared, then we're able to find, okay, that's VF squared equals VI squared plus 2A delta D. All right. Now, again, like I said, it just trying to show you that this is an actual legitly found formula. It is something that we can kind of work with and trust and use. Okay. So when we look at this one, let's run this problem. All right. So we see his initial velocity is 250 meters per second, right? So that thing comes from right there, all right? Because it says that we want to know after this time interval or for a certain time he travels 5,000, then we're seeing a second time, or a second speed there, sorry, okay? Acceleration, 50 meters per second. Notice it says he accelerates. If it said he decelerates, that'd be a negative 50. Because he accelerates, this is 50 meters per second squared, okay? Next number is at delta D. That's 5,000 meters, right? Again, doesn't say anything about going backwards or forwards or anything like that, so we're going to assume it's that. We want to know how fast is Freddie traveling, how fast he's traveling. That's going to be a VF for us, all right? So that's the formula we're going to plug this thing into. So what we'll do is go 250 squared, right? That's our initial velocity, plus 2 times 50, our acceleration, times 5,000. Once you punch those in, we see we get 62,500 plus 500,000. All right, add those two together, we get 562,500. And then I'm going to take the square root to get my VF all by itself. I end up seeing VF is around 750 meters per second. Okay, so we'll run more problems with that. We'll twist these problems on Monday with you and really start to kind of show you all the different forms of this stuff. Okay. Today's quiz, here's what I want you to be aware of, okay? So organize your notes, get them all together, get ready for it by looking at this and being able to say, okay, in a distance versus time graph, what direction is the object traveling? Is it going forward, backward, no movement, positive, negative, no movement, right, left, no movement? Velocity, is it going zero, constant but zero? Is it going increasing, is it decreasing? Remember, constant but zero just means it's still going at the same rate of speed. It's just not on the zero axis. Okay. What is the acceleration of the object? Remember, this means positive is speeding up, negative is slowing down, zero means it's running at a constant rate for our velocity. Which has the fastest, slowest constant speed? Fastest, remember, is going to be that steepest slope. Slowest is going to be the flattest slope for us. Okay. What direction is an object going in velocity versus time? Top half of the quadrant or of the graph, that's going to be forward, positive. Bottom half below the t-axis, negative or backwards. All right. What is the velocity of the object? Again, is it zero? Right on the zero line. Is it constant? Horizontal line somewhere not on the zero. Is it increasing? Going up. Is it decreasing? Going down towards the zero mark. Okay. What is the acceleration of the object? If it's positive, well, then it's increasing the velocity, speeding up. If it's negative, decreasing the velocity and or slowing down. All right, if it's zero, that just means it's constant. Okay. Quizzes are available on your Schoology stuff. Go ahead. Time limit set up for 30 minutes. Check them out. If you got questions, let me know. Otherwise, good luck. Have an absolutely fabulous weekend. All right. Take care. See ya. Bye.